let's take a look at the origin of life question. Again, the idea that life comes from essentially a complex ensemble of molecules through the outworkings of chemistry and physics, chemical evolution. And this idea is basically that, again, on the early Earth, there were conditions that allowed for small gaseous molecules to react to form more complex building block materials for life that in turn began to react with each other to form more complex molecules that would aggregate into protocellular entities that then would evolve to the first true life forms. And some of the evidence to substantiate this idea comes from laboratory experiments that presumably demonstrate that these processes can actually happen. The famous Miller-Urey experiment would be an instance of this. But the thing is that these examples of success in the laboratory that, again, presumably buttress or justify chemical evolution need to be critically evaluated, because in a sense there really are three types of laboratory experiments that scientists have done in addressing the origin of life question. Two of those types of experiments involve simply determining whether or not that chemistry and physics is possible and what is the mechanism that undergirds it. These would be proof of principle experiments and mechanistic studies. And to date, this is where the bulk of the research has been done in the origin of life. And there's been success in demonstrating that in principle, the chemistry and the physics is possible to support chemical evolution. But nobody has really demonstrated with in any kind of compelling way that these reactions and these processes could happen under the conditions that existed on the early Earth. They've not demonstrated geochemical relevance. They've not done successful geochemical simulation experiments. And to do a successful geochemical simulation experiment, you need to make sure that you're looking at the right types of starting materials at the levels that would have existed on the early Earth. You need to be taking into account the types of energy that would be available on the early Earth to bring about these processes. In addition to that, you need to account for the stability of these compounds to make sure that the stability is long enough for the subsequent steps to take place in chemical evolution. You need to make sure that you're taking into account the types of interference, the chemical interference that would have existed as well. So it's a complex experiment to do when you try to do geochemical simulation. There's another factor that also comes into play, and that is researcher involvement. One thing that is different in the laboratory versus the early Earth's condition is the existence of chemists. Okay, on the early Earth, there were not chemists that were present. But in the laboratory, chemists are the ones who are carrying out these origin of life laboratory experiments. And they are involved in doing so. And the question is, how much of their involvement is legitimate towards establishing chemical evolution? Now, obviously, the experiment isn't going to happen if a chemist isn't in the lab setting up the apparatus, adding chemicals, withdrawing aliquots of the reaction to analyze what's happening throughout the course of the process. So there's some involvement that is absolutely necessary by definition to do the experiment. But the question is, at what point does that researcher involvement cross the line and no longer become legitimate, makes the experiment artificial? Is it legitimate to control the pH, to control the temperature? Is it legitimate to vary the order of addition, the timing of addition of reactants, the removal of products? When do you stop the reaction? These can all influence the outcome of the experiments and make what should be failure success in the laboratory. Let me give you an example of where this plays out. The RNA world's hypothesis is the leading explanation for the origin of life. And this idea basically says that the very first biomolecules were RNA molecules. There's an entire biochemistry based around RNA, and that this RNA world, as it's called, invented over time the contemporary DNA protein world that we see in biochemical systems. Now, part of the evidence to substantiate this idea, not the sum total of the evidence, but just a small sliver of the evidence, is the fact that researchers can go into the lab and can assemble RNA molecules from building block materials on clay surfaces. And so the argument is this process could have happened under the conditions of the early Earth, because in the laboratory we can make fairly long RNA chains again, using clay as a catalyst to bring these building block materials together. And on the surface, it seems rather compelling. until you begin to analyze what is involved in terms of doing these experiments. First of all, when these experiments are done in the laboratory, researchers are careful to exclude interference that would essentially frustrate or shut down the chemistry. And these interference that are eliminated from this experiment or excluded from the experiment most certainly would have existed on the surface of the Earth at levels that probably would have interfered with the chemistry and made it impossible. In addition to that, researchers are very careful to stop the reaction before the RNA molecules get too long, because if the chain length gets beyond 50 subunits in length, it becomes irreversibly adsorbed to the clay surface. And so researchers are careful to stop the reaction before that happens in the lab. Also, researchers in order to get this reaction to work, have to use the right type of clay from the right location on Earth. They have to treat the clay in a very special way. And in order to get RNA molecules to form, they have to use activated subunits, which most definitely would not have existed on the surface of the Earth. In other words, this experiment is only successful because an intelligent agent has orchestrated the conditions in such a way to make the reaction work. And it's not a geochemically relevant reaction. And this is what Paul Davies has said with regard to these types of experiments. As far as biochemists can see, it is a long and difficult road to produce efficient RNA replicators from scratch. This conclusion has to be that without a trained organic chemist on hand to supervise, nature would be struggling to make RNA from a dilute soup under any plausible prebiotic conditions. Or, as Simon Conway Morris has said, many of the experiments designed to explain one or other step in the origin of life are either of tenuous relevance to any believable prebiotic setting or involve an experimental rig in which the hand of the researcher becomes, for all intents and purposes, the hand of God. So I think that I'm justified in expressing skepticism about chemical evolution based on the work that's been done to date trying to justify chemical evolution using laboratory studies. And I would actually argue that that skepticism actually provides us with powerful evidence that apart from an intelligent agent, life is not possible. Life could not originate. What about skepticism about macroevolution? Well, when I look at the patterns in life's history, I see things that trouble me, that seem to be incompatible with evolution explaining the history of life on Earth. Let me give you one pattern that I'm troubled by. And this has to do with the idea that the evolutionary process is historically contingent. As Dr. Rainbow showed us, that the first step in any evolutionary scenario is a mutation, a change in the sequence of DNA molecules. And those changes, for all intents and purposes, could be viewed as being random changes, though they probably, in a strict sense, aren't random, but they're random variations in the DNA sequence that are operated on by the forces of natural selection. But evolution doesn't involve a single mutation and a single exposure to selection forces, but rather it's a sequence of chance events operated on natural selection, a sequence of contingent events. And the evolutionary process is historically contingent. And this means that the evolutionary process should never repeat itself, because the likelihood of being able to repeat a historically contingent sequence of events is highly remote. In fact, Stephen Jay Gould popularized this idea in his book, A Wonderful Life. And this represents, in my mind, a test for evolution. Do we see contingency as being the pattern in the record of nature, or do we see repeatability? Now, the idea of historical contingency as defining the evolutionary process is well established. There have been computer simulation studies showing that, again, macroevolutionary processes seem to be historically contingent. Or the long-term evolution experiment done looking at E. coli, showing, again, that at a biochemical level, what would amount to microevolutionary changes are historically contingent. So this really appears to be the way evolution operates, or putatively operates. Yet what we see when we look at the record of nature is that convergence is widespread. At an organismal level, as Simon Conway Morris documents in his book Life Solution, we see hundreds and hundreds and hundreds of examples where it looks as if evolution has repeatedly generated the same outcome time and time again in terms of anatomy, physiology, and behavior. And the problem that I have with it is that the examples of convergent are so frequent that this becomes almost a defining pattern within the living realm. And the structures that are convergent, that appear to have originated independently multiple times, are incredibly complex, making it difficult to envision how they could have originated one time, let alone multiple times independently. And we even see convergence at the molecular level. And in fact, the most remarkable example of convergence that I've come across is DNA replication. DNA replication is a central process in biochemistry, and it is an incredibly involved process at a molecular level. And it turns out that DNA replication in archaea, which is a major division of prokaryotic organisms, and eubacteria is for all intents and purposes the same. Yet it looks as if, from an evolutionary standpoint, DNA replication would have had to have emerged independently 2 separate times in archaea and in eubacteria. And to me, again, that just doesn't fit. And this is what Bill Schaaf has said about what we should expect with regard to the natural history of biochemical systems. Because biochemical systems comprise many intricately interlinked pieces, any particular full-blown system can only arise once. Since any complete biochemical system is far too elaborate to have evolved more than once in the history of life, it is safe to assume that microbes of the primal last common ancestor cell line had the same traits and characteristics same characteristics as its present-day descendants. And this would include DNA replication. That was the expectation, that DNA replication emerged in the primal cell line. But this is, in fact, not the case. It seems to have emerged independently 2 separate times. And so this is a reason why, again, I'm skeptical about macroevolution. This is just one reason. But again, this idea of repeated origins fits nicely within a model that would look at a creator being responsible for life's history, because designers reuse good designs over and over again. Why wouldn't the creator?